Good afternoon, everyone. We're Group 1 and we are assigned for the assignment number 1. Here are the members of our group. First is Magbitang Ronald Matthew, Mendoza Jonas Cyril, Nijjar Rohit, Sanglay Joshua Ray, and I am Jerome Richard.
Chapter 2, problem number 38. It's determine the magnitude of the current flowing through a 4.7 kilo ohms resistor if the voltage across it is for letter A 1 millivolts, for letter B it's 10 volts, and for letter C is 4e raised to negative t volts, and for letter D it's 100 cosine of 5t volts. And for the letter E is negative 7 volts. For the following answers, we got for letter A using the formula for current, which is equals to voltage over resistance, we got 1 times 10 raised to negative 3 volts over 4.7 times 10 raised to 3 ohms. It's equals to 2.12 nanoamperes. For letter B, using the same formula, we got 10 volts over 4.7 times 10 raised to 3 ohms equals to 2.3 milliamperes. And for the letter C, we got 4e raised to negative 3 volts over 4.7 times 10 raised to 3 ohms equals to 851 e raised to negative t microamperes. Then for the last one, 100 cosine of 5t over 4.7 times 10 raised to 3 ohms is equals to 21.28 cosine of 5t milliamperes.
For Chapter 2, Question 48, here is the problem. For each of the circuits in Figure 2.38, find the current I and compute the power absorbed by the resistor. Here is the Figure 2.38. To solve this one, we will be using the formulas for current and power absorbed, which is I is equals to V over R and power absorbed is equals to V squared over R. Going back to the figure, we will solve this first, the top left portion. So by substituting, you can see the voltage supply is 5 and the resistor juice is 10 kilo ohms. Going back, by substituting, I is equals to 5 over 10 times 10 to the cube is equals to 500 microamperes. And power absorbed is equals to 5 squared over 10 times 10 to the cube, which will give an answer of 2.5 milliwatts. We will be using this throughout the given circuits. So for the top right portion, which is this one, we will be using again the same formula by substituting I is equals to negative 5 over 10 times 10 to the cube is equals to negative 500 microamperes. For the power absorbed is equals to the quantity negative 5 squared over 10 times 10 to the cube equals 2.5 milliwatts. For the bottom left, again by substituting I is equals to negative 5 over 10 times 10 to the cube, I is equals to negative 500 microamperes. Again, for power absorbed is equals to negative 5 squared over 10 times 10 to the cube, which will give us 2.5 milliwatts. And for the last one, the bottom right, I is equals to negative 5 over 10 times 10 to the cube is equals to 500 microamperes. Power absorbed is equals to the quantity negative 5 squared over 10 times 10 to the cube is equals to 2.5 watts. As you can see, the powers used is all the same of 2.5 watts. All of from top left, top right, bottom left, and bottom right. While the top left to the bottom right currents varies because of the supply used. Like for this one, for the top left, you can see it came from the positive sign going to the left to the negative sign, while the top right come from the negative to the positive side.
Good day, I'm Jonas Cyril Mendoza, and today I will discuss to you my designated number. Chapter 3, number 2. Referring to the circuit depicted in figure 3.5, count the number of nodes elements and branches. So this is the figure in number 2. There are 4 nodes exactly, which are 1, 2, 3, and 4. There are 7 elements in this figure, which is 1, 2, 3, 4, 5, 6, and 7. Lastly, there are 6 branches. 1, 2, 3, 4, 5, and 6. We omit the 2 ohm resistor as it is not associated with 2 distinct nodes. So this is the answer. Second, chapter 3, number 6. A local restaurant has a neon sign constructed from 12 separate bulbs. When a bulb fails, it appears as an infinite resistance and cannot conduct current. In wiring the sign, the manufacturer offers 2 options. From what you've learned about Kirchhoff's current law, which one should the restaurant owner select and explain? So these are the choices. The number 1 is in a series connected bulb, and the second one is a parallel connected bulbs. So what we'll learn is that the parallel connected option is more safe rather than the series connected option because it would allow most of the sign to still light, even if 1 or more bulbs burn out. For that reason, the owner should select the parallel connected option.
For number 16, we are given the circuit of figure 3.57. The figure 3.57 is given on the right. So in this problem, we determine 4 voltages. For A, we determine the voltage V1 if V2 is equal to 0 and V3 is equal to 17 volts. For B, we determine the voltage V1 if V2 is equal to 2 volts and V3 is equal to 2 volts. For C, we determine the voltage V2 if V1 is equal to 7 volts and V3 is equal to 9 volts. Determine the voltage V3 if V1 is equal to 2.33 volts and V2 is equal to 1.70 volts. So from the given figure, we are able to form the equation of negative V1 plus V2 minus V3 is equal to 0. So from this equation, we can solve for V1 and use that equation to substitute the values 0 and 17 to obtain the value of V1, 17 volts. For B, we solve for V1, we substitute the given V2 is equals to 2 volts and V3 is equals to 2 volts to the equation, giving us an answer of negative 4 volts. For C, we substitute the values 7 volts and 9 volts to the equation for V1 and V3, giving us 16 volts. For D, we also substitute 2.33 volts and 1.70 volts for V1 and V2, giving us an answer of 0.63 volts.
For chapter 3, number 22, consider the simple circuit shown in the figure 3.62 using Kirchhoff's voltage law and derive the expressions. Voltage source, which is negative, plus voltage across resistor number 1 plus voltage across resistor number 2 is equals to 0. Transposing voltage source to the other side, it is now equal to V1 plus V2. But remember, V is equals to current times the resistance. So voltage source now is equals to the current across resistor number 1 multiplied by the resistance across resistor number 1 plus the current across resistor number 2 plus the resistance across resistor number 2. Since it is in a series connection, V source is equals to R1 plus R2 multiplied by the quantity of the current. Solving for the current now is equals to voltage source over the quantity of R1 plus R2. And let this be equation number 1. The other way of computing for the current is also equals to voltage 1 over resistance 1, and the other one is voltage 2 over resistance 2. That is be the equation number 2. Combining the two equations in terms of I, it will become V1 over R1 is equals to voltage source over R1 plus R2. And V2 over R2 is also equals to voltage source over R1 plus R2. Isolating the voltage 1 is now equal to the product of voltage source and resistance number 1 over the quantity R1 plus R2. And voltage number 2 is also equals to voltage source times resistor number 2 over R1 plus R2. With this, we prove that the derived equations are correct.